Remember back to our mechanics class, every time we hit a force that was a conservative force. What is a conservative force? When the work done between any 2 points by that force is independent of the path taken. You can take this path to get from A to B, you can take this path, you can take some other path, any path to get from A to B. If the work done by that force is the same for any path, it's a conservative force. The first one we saw was gravity. The gravitational force was a conservative force. The second one we saw was a spring force. It's also a conservative force. And every time we have a conservative force, we come up with a potential energy term, because potential energy just depends on the endpoints, and we don't care how we got from one point to the other. We just care about where we started and where we ended up. And potential energy is a very convenient thing to use when we solve problems. If we're talking about the spring force, the magnitude of the spring force is just kx. We integrate that because we look at the work done by the spring force. The integral of f dot dx is the work done, and we get 1/2 kx squared. So we came up with a potential energy term, an equation that we could always count on. 1/2 kx squared is what we use for spring potential energy. Let's take a look at what we got for gravity. For gravity, we had two situations. If we were close to the surface of the Earth, we treated gravity as a constant force, and we got a potential energy that was mgy. But if we were far away from the surface of the Earth and we allowed the force of gravity to change, then we got a different potential energy, negative g m1 m2 over r. So we have two formulas there. We have to figure out which situation we're in. Are we close to the surface of the Earth and we're treating gravity as a constant force? Or are we taking into account that gravity is changing because we're moving away from the surface of the Earth? Or maybe it's not even the Earth at all. It's two other massive objects out in space, and we want to know what the potential energy is between them. We can use the general term for the potential energy, negative g m1 m2 over r. So students then are thinking, well, I've got this one equation for spring potential energy. I've got a couple for gravitational potential energy. What's the equation for electric potential energy? Because I know the electric force is a conservative force, and it makes sense whenever I have a conservative force to come up with a potential energy term. Well, we don't have one. And the reason is that we don't have some fixed electric field that's always the same. With the spring force, it's always the same, kx. With gravity, there's only two options, right? It's either constant or it's 1 over r squared. But let's take a look at electric fields. There isn't a specific formula for an electric field. We can create charge distributions that create all kinds of different electric fields. We can create an electric field that's constant. By having an infinite sheet of charge, it creates a constant, uniform electric field. We can have an electric field that drops off as 1 over r. By creating an infinite line charge, instead of a sheet of charge, we make it a line charge, and now the electric field drops off as 1 over r as we move away from it. We can make an electric field that drops off as 1 over r squared when we're outside of a spherically symmetric charge distribution. We can make an electric field that's proportional to r when we're inside of a uniformly distributed spherical charge distribution, right? All kinds of different complicated charge distributions would create different electric fields. These are just a few. So we don't have a specific one. It's not like a spring where it's always the same, or gravity where we only have two options. It's always different. So we need a general way of finding the potential energy. To find the electric potential energy, we're going to use the fact that the work done is negative delta U. This is how we defined potential energies in the past. We found the work done by the spring force and said, let's set that equal to negative delta U, and we came up with the spring potential energy 1/2 kx squared. We did the same thing for the force of gravity when it was constant, and we got mgy. When it was the general form for the gravitational field, we got negative g m1 m2 over r. We used this form. We found the work done by integrating f dot dx and setting it equal to negative delta U. We also know from our definition that the work done by the field is negative q delta v. I'm going to write here work done by the field. When we move charges in an electric field, the field is going to do some work on that charge. Oftentimes, we reach in with some external force and do work also. And we have to differentiate and think about which work are we finding. This is the work done by the field. Let's take a look at gravitational potential energy. We all understand that if we have a massive object like this pen, and I'm holding it at a certain height, it's got some gravitational potential energy because of its position in the gravitational field. And if I raise it up higher, it has more gravitational potential energy because of its new position in the gravitational field. How do we know it has more energy? Well, let's think about this. If I dropped this object from the lower height, it's going to move in that direction. And before the split second before it hits the earth, it's got a certain amount of speed. If I lift it up to a new height and I drop it from this higher height, it's going to move through the gravitational field a longer distance, which means the gravitational force is going to do more work on my object that's falling. And so the split second before it hits the earth, it's going to have a much higher speed, a much higher kinetic energy, because the force of gravity acted on it over a much longer distance. And if it hits the earth with more kinetic energy, then it had to have started out with more stored energy, with more potential energy. So the higher up it is in the gravitational field, the more stored energy, the more gravitational potential energy is in our system. We all understand that, I think. So let's take a look at an electrical field and kind of use the same reasoning to think about where the charges have the most potential energy. I've drawn a uniform electric field, a constant electric field pointing down on my paper. And I'm going to imagine a floor here. I'm going to put an imaginary floor here. And I've got two positive charges. One, I'm holding a little bit above the floor, and the other one I'm holding much higher up above the floor. When I let go of the lower charge, the electric force pushes it in that direction, and it starts moving in that direction. And the split second it passes my imaginary floor here, it has a certain speed, a certain kinetic energy, because the electric field did some work on it and got it moving and gave it some kinetic energy. If I raise that particle up to a different position in the electric field, and I let go of it from there, the force from the electric field acting on our charge will act over a much bigger distance. It will do more work on the charged particle. And so the charged particle will gain more energy. It will be moving faster when it passes my imaginary boundary here. That means it has more kinetic energy at that point than the other one. So it must have started out with more stored energy, with more electric potential energy by virtue of its position in the electric field. Think about that when you're trying to figure out what situation has more stored energy, what situation has more potential energy. It's a little trickier with electric fields because we have both positive charges and negative charges. That's why I say go back to basics. Draw an imaginary line in your system and let go of the particle and see how much speed it would have when it crosses that boundary. And oftentimes you can think through and reason through and figure out what situation has more stored energy and which one has less. Let's see what happens as we bring multiple charges in and create a system of multiple point charges. We want to know how much energy does it take to put that system together, or how much energy would we get out if we allowed those charges to go infinitely far apart from each other. I'm going to do an example with 3-point charges, Q1, Q2, and Q3. We've got these 3-point charges infinitely far apart from each other. They don't interact with each other. And I'm going to bring Q1 in from infinity. And because there are no other charges around, I don't do any work. There's nothing, no field there that I'm fighting or no field there that's helping me. I don't do any work moving that charge in from infinity because there's no other charge there to interact with. That means I have no stored energy. There's no potential energy because I just have one charge. I need a system to have potential energy. I need at least 2 charges or a field and a charge. Here I just have one charge, so there's no stored energy. It didn't cost me anything to bring that charge in, and I'm not going to get anything if I just let go of it or move it out. Now let's bring Q2 in. We brought Q2 in, and it's a distance R12 away from the other charge. And this time we had to do a little bit of work because there's a charge there that's interacting with it. If they're the same sign, we had to do positive work. We had to push Q2 in because it's being repelled by Q1. And if they're opposite signs, we had to do negative work because it's being attracted and pulled in faster and faster and faster toward Q1, but we had to slow it down and stop it a distance R12 away from Q1. So we had to do negative work on it. So either way, whether this charge is positive or negative, we had to do some work on it. And there's some stored energy in this system. How do we know the energy? It's the charge that we moved, Q2, times the potential difference between where it started and where it ended up. And from point charges, we all have the understanding that the potential at infinity is 0. So that's why I just wrote V1 here. This is the potential at this location, the location of Q2, due to Q1. So this comes out to be K Q1 Q2 over R, the distance between the two of them. Now we bring the third charge in. And we have a distance between these two charges of R23, and we have a distance between these two charges of R13. When we bring Q3 in, it's interacting with both Q1 and Q2. Maybe they're both repelling it. Maybe all 3 of these charges are the same sign, and both Q1 and Q2 are repelling it. Maybe they're both attracting it. Maybe there's a combination. Maybe one of these charges is attracting it and the other one is repelling it. But either way, we're doing some work and we can figure that out. Even if it's 0, it might be 0. Maybe one of these charges is attracting it, the other one's repelling it, and it turns out that it all cancels to 0. We didn't do any work bringing Q3 in from infinity, but this equation will tell us. The potential energy for our third charge is going to be its charge times the potential at its final location, because we knew it started out at V equals 0. And the potential is a combination now of the potential from charge 1 and the potential from charge 2. So what I get here, K Q1, and I add all of these up, and I get my total U for the system of charges. And it turns out it's every combination, K, Q1, Q2 over R12, K, Q2, Q3 over R23, K Q1 Q3 over R13. It's the sum of every combination. And these U's, this is important, can be positive or negative. You must use the correct sign in here for your charges. Must use the correct sign for the Q's. If Q1 is negative, you put a negative number in there. If Q2 is positive, you put a positive number in there. When you multiply a negative times a positive, this becomes negative. Make sure you put the correct sign in. Typically, when we're dealing with scalar quantities, and of course energy is a scalar quantity, signs are very important, and you have to have the right sign in there. And when you're dealing with vector quantities, the sign just tells you the direction. And so typically we're dealing with magnitudes, and you have to think about the situation to get the sign correct.